Hello, welcome to the final exam review. The final exam is going to be quasi-comprehensive. It's not going to cover everything we've talked about in the class. The exact topics that'll be on the test will be you can find on the final exam review sheet. But generally those topics are going to come from chapters 1 through 7, or in terms of tests, they'll be on from topics from tests 1 to 3. There's not going to be any hypothesis test questions because we just took a test over hypothesis testing, so we're not going to review that at this time. But the reason for the final exam, or one reason, is to go back and look at those topics that we covered earlier on in this semester, kind of refresh our memory on some of those ideas, and to briefly talk about how they relate to some of the things that we've been doing here in hypothesis testing. So a reminder of what you can use for the test. For the test, you can use really any table that you want. Specifically, we can use table A6, which is a table of critical values for regression. There's your z-score table, table A2. There's a critical t-score table, table A3, that we use for constructing confidence intervals for means. We don't need any of those hypothesis testing tables because there's not going to be any hypothesis tests. And then, as always, you can use your calculator and any handwritten notes that you want. No electronic aids other than your calculator are allowed. So the first set of topics we're going to review here come from Test 1, which covered chapters 1 through 3. So chapter 1, we had a bunch of important definitions. Here let's just briefly review 4 of the most important definitions. The first 2 were the definitions of a population and the associated parameter. So a population is the complete collection of all elements to be studied. It's this large group of people or items that we're interested in. A parameter is some numerical measurement that we obtain from surveying every member of the population. Now remember, the word surveying is a generic term meaning that we got the information that we wanted. So if we go out and we interview every single person in our population, and then we calculate a number like a mean or a proportion or a standard deviation, that number is what we would generically call a parameter. Now similarly, we have the word sample and statistic. A sample is a subcollection of members from a population, and then a statistic is some numerical measurement obtained from surveying every member of the sample. So if we go out and we survey just a small portion of our population, and then we calculate a mean or a proportion or standard deviation or something like that, that number is what we generically call a statistic. Now, as we've stressed throughout the semester, the difference between a population and a sample, and a parameter and a statistic, is what the field of statistics is really all about. We want to know something about a large population. That means we want to know something about, or we want to know the value of a parameter. But that's impossible to know because it requires us to go out and get information from every single member of the population. So instead, we get information from a sample, and based off that sample we calculate a statistic, and then we use that statistic to try to draw some conclusion about the larger population. Okay? So these ideas are very, very important to the field of statistics. Okay. So in chapter 2 we talked about some different types of graphs. One of the most important types of graphs is a histogram, and a histogram looks like this, where on the horizontal axis we have our different values of our different data values, and the vertical axis is our frequency or relative frequency. So for instance, this histogram tells us that we have one data value that's at about 120. We have 4 data values that are at about 135. We have 7 data values about 150, so on and so forth. And one important thing that the histogram gives us is the shape of the data. Specifically, we like to see this bell curve looking shape, where we start low, increase to a high, decrease to a low again, and the graph is roughly symmetric. Whenever we see that, we say that the data have a normal distribution, and as we saw later on in the semester, a normal distribution is very important. So we should be able to construct a histogram and be able to identify if that data have a normal distribution or not. So in Chapter 3, we started crunching numbers and calculating statistics. And one category of statistics that we calculate are what we call measures of center. And there were 4 different measures of center. The first, the most common, is the mean, where we add up all the data values and we divide by n. And we typically denote that mean with the symbol x bar. And then we have the median, which is the middle value when the data is arranged from largest to smallest. So the median, you line them up from smallest to largest. You pick the one right in the middle. And then the mode is the value that occurs most frequently. So we should be able to calculate all of these different measures of center. The next category of statistics that we calculated was called measures of variation, and we had 2 of them. The first one was called the standard deviation. And informally, standard deviation is a measure of how spread out the data are. If your data values are all pretty close together, then you're going to have a fairly small standard deviation. If there's a lot of difference in the data values, then you're going to have a large standard deviation. Now, here was the formula, but we never really used that because we let the calculator do all the number crunching. The other measure of variation was called the variance, which we denoted by s squared, and the variance is simply the square of the standard deviation. And so to calculate the variance, you first calculate the standard deviation, and then you square it, and you're all done. Okay. Now remember that these formulas for these different calculations are all built into the calculator. So you enter your data in a list, then you go to the calc menu and choose the first option, 1 var stats, and it will calculate your mean, your median, standard deviation. You still have to do the mode and the variance with a little more work, but those aren't terribly complicated. So always let your calculator do the work when calculating these statistics. Now, one way we use the standard deviation is with what we call this empirical rule. This empirical rule applies to data with a normal distribution. And the empirical rule says that 68% of our data values are within 1 standard deviation of the mean. So we have this range here that goes from the mean minus the standard deviation to the mean plus the standard deviation. Empirical rule says that about 68% of our data values are between those 2 numbers. And then the empirical rule says that 95% are within 2 standard deviations. So we have this wider range of values. 95% of our data values are within those between those 2 numbers. And then likewise, roughly all or almost all of our data values, 99.7, are within 3 standard deviations of the mean. So this is one way that we use the standard deviation, and we should be able to apply this empirical rule to identify what percentage of data value should be between different values. Okay. Now, we had a couple of different types of means. We had a sample mean and we had a population mean. A sample mean was denoted by x bar, and the population mean is denoted by the letter mu, the Greek letter mu. And the difference between these is where the data come from. If we get data from a sample, we add them up, divide by the number of values in the sample, we get a sample mean x bar. If we were to go out and get data from all members of our population, add them all up, divide by the total number of values in the population, we would call that mu. And x bar is an example of a statistic because it's calculated based on a sample. Mu is a parameter because it's calculated based off information from the entire population. So we should be able to identify if a given number is x bar or is mu. And the way we determine that is we ask ourselves, where did the data come from? If it came from a sample, then it's x bar. If the data come from the entire population, then it's mu. Now, one very important thing to remember is that x bar is an estimate of mu. And we saw that later on in Chapter 7 when we talked about estimating a population mean mu. We also saw it in Chapter 8 when we talked about hypothesis test for a population mean. We always start off by calculating a sample mean x bar. We use that as an estimate of mu, and then we either did a hypothesis test or calculated a confidence interval to try to draw some conclusions about the value of mu. Okay. And so in general, a sample statistic is an estimate of the corresponding population parameter. So for instance, a sample proportion is an estimate of a population proportion. A sample standard deviation is an estimate of a population standard deviation, so on and so forth. Another way that we use the standard deviation is with what we call the z-score. We saw a z-score a couple different times. We first saw it in Chapter 3. We also saw it in Chapter 7 when we calculated normal probabilities. And so the z-score in words of a z-score of a given value, x is the number of standard deviations x is from the mean. And so here was our formula for z. We took the x value or the data value, and we subtracted the mean, and we divide it by the standard deviation. So this gives us the number of standard deviations that the data value is from the mean. Now, one way that we use the standard deviation is we used it to identify ordinary and unusual data values. We said that ordinary values have a z-score between -2 and +2. And so if a data value has a z-score that's less than a -2 or greater than a +2, then we would consider it to be unusual. Doesn't mean that it's wrong necessarily, just that it's unusual. So we should be able to calculate z-scores and apply this idea to determine if a given data value is ordinary or unusual. Last thing from Test 1 that we talked about came from Chapter 10. That's the idea of correlation and regression. So remember, correlation is a fancy term for relationship. And so we're asking, is there a relationship between two variables? So in this example, we have a variable of the miles per gallon of a car and its weight. Those are both variables. And so we went out and got some data from a bunch of cars. From each car, we recorded its weight and its miles per gallon. And so we constructed a scatter plot like this and looked for a straight line relationship. Notice that these kind of form a straight line that slopes down from left to right. So we would say that these two variables have a negative linear correlation. Again, correlation means relationship. Linear means they kind of form a straight line. Negative means that line slopes down from left to right. And so it looks like there's a relationship. The next thing we asked is, well, just how strong is that relationship? And so we measured this with a quantity we called R, or the linear correlation coefficient, which takes values between a -1 and a +1. And the closer that we are to either +1 or -1, the stronger the linear relationship. Okay. Now, we had a complicated formula for calculating that, but we didn't have to use it because that formula was built into the calculator with this linreg t-test. So you should be able to use that command to calculate the R value. Okay. And so then we calculated an R value, and we tried to use that information from a sample to answer a question about the larger population. Specifically, the question is there a linear correlation in the large population? Our data came from a sample. If the R value is close to +1 or close to -1, then that indicates that there is a linear correlation in the population. But we want to just determine just how valid is that conclusion. And so we did that by comparing the R value to these critical values, which come from table A6. Now what we're really doing here is a hypothesis test, just like we did in Chapter 8. We didn't call it a hypothesis test at the time, but really this is a hypothesis test. We could have calculated p-values here, and in fact the calculator gives us a p-value. We didn't talk about that p-value at the time. But here we're doing a hypothesis test using critical values rather than p-values. And so we got from our table here, we chose our significance level alpha, which is typically 0.05. We went to n, which was the number of data points, and that gave us our critical value. And then we came to our conclusion by comparing the absolute value of R to the critical value. If R was bigger than the critical value, then we would conclude that there is a linear correlation in the population. If R is less than the critical value, then we conclude that there is not a linear correlation in the population. And so again, what we're really doing there is a hypothesis test. And so in this particular example, we have a rather large R value. It's bigger than our critical value, and so we would conclude that there is a linear correlation in the population of all cars. So that means it makes sense to calculate a regression equation to try to predict values. So our calculator gave us this regression equation. Remember, this regression equation had the form y equal a plus bx, and the calculator gave us the values of a and b. So here was our regression equation, and then if a car weighed, for instance, 3,000 pounds, we could plug in 3,000 for the weight, do the arithmetic, and that would give us a predicted value of the fuel economy. So in general, for a regression, you should be able to calculate the R value, do a hypothesis test just like we did in this example, and then calculate the regression equation and use it to predict values. So that was the last topic from Test 1. Test 2 covered chapters 4 and 5, which dealt with probability. So remember that probability, an informal meaning of probability, is that a probability is a measure of how likely an event is to occur. Probabilities take values between 1 and 0, and we interpret a probability as an average in the long run. Means if we did this activity over and over again, the probability of this event occurring would tell us what would happen if we did it a whole bunch of times. It's not going to tell us what happens on one instance or one trial, just what happens in the long run. And then we said that if the probability is less than 0.05, then we conclude and we consider that event to be unusual. Okay. So we had some different ways of calculating probabilities. The first rule is what we called a relative frequency approximation. And the idea is that you perform the procedure over and over again, record the number of times the event occurred, and then we take the number of times that the event occurred, divide it by the number of trials, and that is an approximation of the probability. Second approach was a little more theoretical. If all the outcomes are equally likely, then we can take the number of ways that the event can occur, divide it by the size of the sample space, and we call that the theoretical probability or the actual probability. Then a law that related these two ideas was called the law of large numbers, which says that as the number of trials gets larger, the Rule 1 approximation gets closer to the actual probability from Rule 2. So in other words, this is kind of a fancy way of saying that the more trials you do, the better your approximation is going to get. So then we had a couple of rules for calculating probabilities of little more complex situations. The first is what we called the addition rule, which said that the probability of one event or a second event is the probability of the first plus the probability of second minus the probability that they both occur. So the addition rule deals with a situation where we have an or and indicates that we add. The second rule is what we called the multiplication rule, which dealt with the situation where we have a probability of one event and a second event occurring at the same time. And this says that we take the probability of the first event times the probability of the second, given that the first has already occurred. And this probability here is what we called a conditional probability, which is the probability of event B taking into account the previous occurrence of event A. So intuitively, what these rules meant is that if we see the word or inside the parentheses, that means we add, but make sure we don't double count anything. If we see the word and, that means we multiply, but make sure to take into account the occurrence of event A when calculating the probability of B. So make sure you take into account that A has already occurred when calculating the probability of B. So you should be able to use these rules to calculate some probabilities. Okay. The next topic is the idea of a probability distribution. And remember that a probability distribution is a description that gives the probabilities for each value of a random variable. It's often expressed in the format of a graph, a table, or a formula. So we saw distributions in all three of these different forms throughout the semester. Okay. One thing that we did with a distribution was to calculate the expected value. And so to calculate expected value, we take each value of x times its associated probability and add them up. We called that the expected value. It's also called the mean. So as an example of these ideas, here's a distribution of a random variable. In the left column we had the possible values of x. In the right column we have the associated probabilities. And so to calculate the expected value of x, we take each x value times its probability, and then we add them up. Okay. Now, one specific type of distribution we talked about was the binomial distribution, which describes a certain type of procedure that meets the following requirements. We have a fixed number of trials. They must be independent. And the third one here is the most important one, that we have two events that we call a success and a failure. And that's where the bi in binomial comes from. We have two events generically called success and failure. Okay. And then with the binomial distribution, we had some notation. We had n was the number of trials, x is the number of successes, p is the probability of a success in one trial, and then p of x is the probability of exactly x successes. Now, we had a formula for calculating binomial probabilities, but that formula was built into the calculator with this binom PDF formula. And so here was the syntax. And so you should be able to use this formula to calculate binomial probabilities when needed. So that was the last topic from Test 2. Test 3, we talked about continuous distributions and normal distributions specifically. So first thing we talked about for Test 3 was two types of random variables, or two types of distributions. We had discrete and continuous. Discrete, the values must be of a certain type, like integers. Continuous, they don't have to be of a certain type. They can take on any value within some range. Chapter 5 we talked about discrete random variables. Chapter 6 we talked about continuous random variables. The first type of continuous distribution that we talked about was a uniform distribution. Uniform distribution means that kind of everything is equally likely. So example we gave in class dealt with this length of the statistics class that always went between 50 and 52 minutes, and no time was any more or less likely than any other. And so here was a graph of what we called the density, or the density curve had a height of 0.5, and so we used areas underneath this density curve to calculate probabilities. So for instance, if we want to know the probability that a class lasts greater than 51.5 minutes, we would go to 51.5, draw a vertical line, shade to the right, and the area of that shaded region is our probability. So the width there was 0.5, the height is 0.5, so the area was 0.25, and that's our probability. So remember, with these continuous distributions, areas underneath the density curve give us probabilities. The second type of distribution we talked about was a normal distribution, and we had two types of normal distributions. First was the standard normal distribution. Standard normal means we have mean 0, standard deviation 1. That's what standard means. Normal means that the density curve is a bell curve. And in this bell curve, we always have the mean right at the 0. And so here is the density curve for a standard normal distribution. So as an example of finding standard normal probabilities, we use this example of these thermometers, which have a mean of 0 and a standard deviation of 1 and a normal distribution. And so we want to find the probability of getting a thermometer that reads less than 1.58. And so the way we did this is we sketched our bell curve, went to 1.58, drew a vertical line, shaded to the left, and that area is our probability. Now to find area, we used table A2, which gives us areas underneath the standard normal density curve to the left of z-scores. And so the way we look this up is the first two digits are on the left, 1.5, and the last digit across the top, 8, so 1.58. And so there was our probability. So that number gives us that area, which is our probability. So that's all there is to finding normal or standard normal probabilities. The next type of distribution we talked about was the non-standard normal distribution. Non-standard means that we have a mean different than 0 or a standard deviation different than 1. And the example we used in class was IQ scores that are normally distributed, the mean of 100, standard deviation of 15. So this is not a standard normal distribution. So for instance, we found the probability that a randomly selected adult has an IQ less than 130. And so if we let x equal the IQ score, we're going to find the probability that x is less than 130. Now remember, we always use the variable z for a standard normal distribution, and then we used x for a more generic distribution. And so the first step was to convert the x value over to a z-score. So here's our formula for the z-score. Basically the same formula as what we saw in chapter 3. We take x, which is the number inside the parentheses, minus the mean, which is given in the problem, divided by the standard deviation, which is also given in the problem. And so we do that arithmetic here, and that gives us a z-score of 2. So then this probability that we want equals the probability that z is less than 2. Now this is a standard normal probability here. So we draw our bell curve, shade to the left of 2. We look up that area from table A2, and that gives us our probability, 0.9772. Okay. Another very important idea that we talked about in chapter 6 was the central limit theorem. Central limit theorem is extremely important for a couple of reasons. Number one, it's got some important practical applications. Number two, it's extremely important theoretically. Much of what we did starting in chapter 8 is based on the central limit theorem. Now we didn't get into exactly how it was based on the central limit theorem, but central limit theorem plays a role in the theoretical background behind just about everything that we did starting in chapter 8. So central limit theorem deals with scenarios where we take random samples of size n from a larger population with mean mu and standard deviation sigma. Now that sample has a mean, which we denote by x bar, and every sample is going to have a little different mean, and so that x bar is a random variable. Central limit theorem tells us three things about that random variable. Number one, it has an approximately normal distribution. Number two, the mean of that random variable equals the population mean. And then third, the standard deviation of that random variable is the population standard deviation divided by the square root of the sample size. So as an example, consider the population of women which have heights with a mean of 63.6 inches and a standard deviation of 2.5. Suppose we select a sample of 20 women, and we want to find the probability that their mean height is greater than 72 inches. And so we're asking for the probability of the mean of a sample. And so that means that we should use the central limit theorem. If a problem ever asks for the probability of the mean of a sample, that indicates central limit theorem. And so use the central limit theorem. We're told that x bar is normally distributed, has a mean equal to the population mean, standard deviation equal to the population mean divided by the square of the sample size, which comes out to be this number here. And then we want to find the probability that the sample mean is greater than 72. That random variable has this mean and this standard deviation, and it has a normal distribution, and so we're dealing with a non-standard normal distribution at this point. So we calculate the z-score, take the number inside the parentheses, minus its mean divided by its standard deviation, which comes out to be this large number, and then we convert everything over to a standard normal distribution, and we look up this area here from our z-score table, and we get our final probability. Okay. So remember, central limit theorem deals with the probability of the mean of a sample. Okay. The last big topic we talked about in test 3 dealt with confidence intervals. And so the idea here is that we want to know a population proportion or a population mean. And so we go out and collect some data to get an estimate of that population parameter, and then we calculate an interval which gives us a range of possible values. And so we talked about a margin of error for a population proportion, and here was our formula. P hat was our sample proportion, Q hat is 1 minus P hat, N was the sample size, and then Z sub alpha divided by 2 was the critical Z-score, which came from table A2. So this gives us our margin of error, and then based off that margin of error we calculate a confidence interval which took on one of these 3 different forms. The form that we like to use the most was this one here. We take P hat minus E and P hat plus E, and that gives us a range of possible values for P. So this is going to be a number, this is going to be a number. That gives us a range of possible values for P rather than just a one number estimate. Okay. Now we could do that by hand, or we could also use this one proportion Z interval command from the calculator. Either way you do it is fine, but be able to calculate a confidence interval for a population proportion. Now, with all of these confidence intervals, we first had to choose a confidence level, which was typically 90%, 95, or 99%. And so one thing we talked about is, what does that confidence level mean? And so a correct interpretation of a 90% confidence level is to say that we are 90% confident that P is somewhere between those two numbers. It'd be wrong to say that there's a 0.9 probability that the true value of P is somewhere between those two numbers. And that's because P is either between these two numbers or it's not. Remember, probability is an average in the long run. Once we have two numbers here, there is no long run. P is either in there or it's not. There's not a probability. So what this 90% confidence level means in a practical sense is that if we were to select many different samples and construct the corresponding confidence intervals, then 90% of the intervals would contain the true value of P. So this is where the long run comes in. If we were to do many different samples, then about 90% of those would contain the true value of P. Okay. The last topic here is the margin of error for mu, which is and confidence interval for mu. Same basic idea as the margin of error and confidence interval for P. And so to calculate a margin of error for mu, from our data we need to have a sample standard deviation, a sample size, and then we get a critical t-value. And so here is our formula. We take the sample standard deviation divided by square root of the sample size, take it times this critical value. Now this critical value comes from this table A3, where our significance level alpha is the area in two tails. So typically we use a 0.05 significance level, so we'd use this column. And the left gives us degrees of freedom, which is our sample size minus 1. So after we calculate the margin of error, we calculate a confidence interval, x bar minus E, x bar plus E. And again, this gives us a range of possible values for mu. X bar is a one number estimate of mu. A confidence interval gives us a range of possible values. This formula for the confidence interval is built into the calculator. Option 8, the t-interval. And so you should be able to calculate a confidence interval for a population mean. Okay. So that's it for this review. So it's a little bit lengthy. But if you want more information on some of these topics, you can go back and look at either the test 1, 2, 3, or 2 or 3 review slides. You can go back, look at those review problems if you really wanted to. But the best way to review for the final exam is to do the final exam review problems on MyMathLab. If you can do those, then you should be in good shape for the final exam.